Okay, this is the second installment of our discussion of repeated measures ANOVA. Some of the material we'll cover here is a little bit more general, does not only apply to repeated measures ANOVA, but we'll use an example of a repeated measures ANOVA to illustrate. So these are the learning objectives. We'll perform a Fisher's LSD protected t-test for multiple comparisons after repeated measures ANOVA. This is something that you've done before for a one-way ANOVA. It's the same formula, just showing how to do it as an example. And then we'll talk about another measure of effect size called Cohen's D, which is used to compare means and the effect, the size of the difference between means. And this is used across multiple tests, but we'll show an example from a repeated measures ANOVA as well. Okay, so multiple comparisons. You remember this is something that you can do post hoc, some pairwise comparisons post hoc. With an ANOVA, you're comparing more than three means, three or more means, and you'll do kind of an omnibus test at first, which gives you an F statistic. If it's a big F statistic, it will have a small p-value associated with it. And if it's smaller than 0.05, then you can conclude that it's statistically significant, reject the null hypothesis. The null hypothesis being that all the means are equal. So you can then conclude that at least one of the means is different from another one. Now, there may be situations in which you don't need to do multiple comparisons at all. That's really all you want to know, just that there is an effect of whatever independent variable you're investigating, like an effect of time, if you're taking multiple measurements over time on individual subjects, for example. But sometimes you do want to know, you kind of want to tease that apart and see where is the effect, where do the means actually differ. So Fisher's LSD protected t-test is a good one to use. Remember, this is only, you only want to use this if the F statistic is significant. If it's not significant, then you can't use this one. But if it is, then you can use this one. And if you're doing three comparisons, then it's fine to just do it without any additional correction. Otherwise, you'll want to use Bonferroni correction, so divide your alpha by the number of comparisons that you compute. And you'll still do that with Fisher's LSD t-test. You'll still perform multiple of those. So here's an example that we talked about in the last lecture. These are the depression scores before and after an earthquake. Here you can see the means for the weeks, and it's across 5 weeks. Week 0 kind of being the baseline prior to the earthquake. Okay. And this is the summary table from the repeated measures ANOVA. You can see we have a significant F statistic. And if we want to do a post hoc comparison, it doesn't make a whole lot of sense to compare each of these with each other to see where they're significant. At least that's not what it says in the textbook. Maybe you'd have maybe you could think of a good reason too, but the way that it does the multiple comparison is really just one comparison, is just looking at the average of all the post earthquake scores. So averaging these four means together to get 10.89 and comparing that to the pre scores. And then here's the Fisher's LSD test. You got 8.68 right here minus this score. And the order of this is not important. You might end up with a negative or a positive here. And then you plug in mean square error, 1 over the two sample sizes. Here you got 4 weeks times 25, so it'd be 1 over 100. And you multiply the mean square error, which you can see right here, times that, take the square root of all of that, and then you get minus 4.54. Now, what do we use for the degrees of freedom? A t-statistic has a certain number of degrees of freedom. Here you would use 96. Okay, so the degrees of freedom associated with the error, mean square error. Or in your Excel output, this would be the within groups variation, the degrees of freedom associated with that. Okay, now how do you get a p-value in Excel? And this is something that I kind of just learned recently, that you can plug in a t-statistic and get a p-value in Excel, basically treating it like a t-table, except it gives you an exact p-value. And it's the t.dist.2t function. Okay, and this is in your help doc now. So our t-statistic was 4.54. And the degrees of freedom was 96. Now notice I didn't put in negative 4.54, I just put in 4.54. So you want to just put in the absolute value. It doesn't accept negative numbers. So put in 4.54 comma 96, and then it gives you your p-value, which you can see is quite small. Okay, so that's how you can get an exact p-value to report in a write-up, okay, from a Fisher's LSD test. Oh, and I should mention, I'll provide you with some guidance on like what multiple comparisons are actually meaningful and which ones we want to do, how many, and yeah, so you can, if you need to do Bonferroni correction, you can know that and how many comparisons you'll need to divide your alpha by. Okay, so effect size. This is kind of again, this is kind of a standard measure of weirdness that we've talked about before. Here's the formula, and hopefully you can see some similarities to a z-score where you have two averages that you're subtracting up on top and then dividing by a standard deviation. Okay, so this is kind of just telling you how many standard deviations apart are these two means. What's the distance and standard deviations? And really, this provides you a standardized measure. If these are depression severity scores, even if someone's not familiar with like what a couple points on a depression score really means, if it's 2 or 10 or 12, that's going to mean different things depending on what kind of a scale you have. But this allows you to standardize it, and then you can say, well, it's this many standard deviations. Kind of like when we were comparing ACT versus SAT scores before. In this case, you're not doing that. You're comparing, depression scores with depression scores, but you can put that distance, like an increase in 2 points for an ACT score might mean more than a increase of 5 points on an SAT score, right? But you can standardize those and put them in by dividing by the standard deviation, and then you can see what that effect size is in a standardized way. Okay, so it's a very simple formula: 2 sample means divided by the standard deviation. Now, here's where it gets a little trickier, is you need to know what do you plug in for S, okay? Because this sample has an S and this sample has an S, so which one do you do? And it really kind of depends, and this is where it gets a little less well-defined. But sometimes it's the pooled standard deviation across both samples. You just like take, highlight both columns and take the S. For both the stdev.s function. If you have a control group, sometimes you want to take typo there. Sometimes the standard deviation of the control group sample. Sometimes you'll use the square root of MS error. That's something that you might do when you're doing a one-way ANOVA. It's not always a clear distinction. Okay, so I'll be specific on assignments. I'll let you know which one you should use. For repeated measures ANOVA divided by the MS error. I'm sorry, another typo there, left out error, but the MS error. it takes out the individual differences, and sometimes that makes an effect size bigger than might actually be realistic, just because individual differences do exist in the real world, and it might not make a whole lot of sense to just like completely take those away. So at least the recommendation from your textbook, and I'm sure you could find differing recommendations in the literature, it's usually better to use the sample standard deviation from a control or baseline group. Okay. So in our case, and this is what they do in the textbook, they take 4.14 is the standard deviation of this column of data here. Okay, the pre-earthquake scores, so the pre-earthquake standard deviation, and then they just do the subtraction. And the convention is to do the bigger one. Yeah, you can see you could have a positive or a negative, but it really kind of depends on how you want to structure it. I think you can have negative effect sizes. I don't think there's anything wrong with that. Here in this case, we've done post minus pre. Okay, so this is looking at what's the size of the increase in depression severity scores, which makes sense. Based on this study, we'd want to look at kind of the increase after an earthquake, would hypothesize that there's an increase. Yeah, if it's something that's looking at a decrease, maybe you'd want to do pre minus post. And then, so this is the degree of the increase in depression severity scores, 0.53 standard deviations. And this is the post-quake right here. So this is the means for, the mean of all these four means, okay? Or if you take all of this data and take the average, select all of those columns in Excel, you get the same number, okay? Oh, and yeah, there's that. I don't know if you really needed anything from there, but... So yeah, post-quake scores are 0.53 standard deviations higher than pre-quake scores on average is how you would interpret that. Okay, all right, that's it.